Hi guys, this is Dr. Anna, and this is the second segment of the first module in historical geology, geologic time. The next person you will have to know in the early concept of geologic time is George Cuvier. He lived between 1769 and 1832. He was the person who founded vertebrate paleontology as a scientific discipline. He also firmly established the fact of the extinction of past life form. I want you to watch this movie about him.
Georges Cuvier was a naturalist, zoologist, and he's considered the father of vertebrate paleontology, but most of all, he was a survivor. When the French Revolution came sweeping through his country, upending centuries of monarchical rule, Cuvier escaped the worst of it, hidden away in a remote corner of France, spared the upheavals that had killed so many of his fellow citizens, and that had led to the disappearance of systems of thought that had reigned for centuries. One of these systems of thought that was disappearing at the time was the idea that the earth was changeless and perfect. Since biblical times, people believed that God had created the earth in a week's time. Every ocean and continent, every animal and plant, and the ancestors of all humanity were created in mere days, without exception and without error, just as they were today. It was simply unthinkable for any one of God's creatures to go extinct, because that would mean that God's creation had somehow been imperfect. Extinction not only seemed out of the question, it was blasphemy. But in Georges Cuvier's time, this idea was undergoing a revolution itself. The bones of animals no living human had ever seen were being found in rock slides and at the bottom of coal mines all over Europe. While some of these fossils did bear some resemblance to familiar animals, some had no living counterparts. And if a fossil seemed to have no living equivalent, the consensus was that it was merely the remains of an animal that no one had seen yet, hidden away in some remote corner of the world. This idea was so prevalent, President Thomas Jefferson had tasked explorers to bring back evidence of living American mastodons, prehistoric elephants similar to mammoths. He was convinced they must be alive somewhere in the uncharted American West. Cuvier sought to overturn this idea once and for all by proving that these were the bones of animals that were no longer around. Through his detailed studies of both living and extinct animals, Cuvier would not only prove that Indian and African elephants were distinct species, he would prove that woolly mammoths and American mastodons were distinct species, without any modern counterparts. Cuvier argued that these animals were much too big to have gone unseen, too conspicuous to have avoided detection. Cuvier went on to prove that many fossil animals were no longer around, including the bizarre giant ground sloth and the massive seagoing reptile Mosasaurus, making the once unthinkable idea of extinction undeniable. The concept of extinction may have been accepted by the scientific community, but just what mechanisms caused an animal to disappear forever were still up for debate. Charles Darwin's theory of evolution was still a few decades away, and while some scientists of the time tinkered with the idea that animals might change over time, Cuvier still believed that animals remained more or less the same as they'd always been. Therefore, he reasoned, extinctions must be brought on by great and temporary changes in the Earth's environment, planet-wide catastrophes, or revolutions, as Cuvier liked to call them. Extinction was the natural consequence of these periodic upheavals, and just as the French Revolution had led to the extinction of France's monarchy and the archaic social systems that entailed, Cuvier's revolutions led to the extinction of the mammoth. But with the discovery of evolution and natural selection, Cuvier's theory of revolutions fell out of favor for more gradual theories of extinction. Extinction operated at the pace of evolution, and species merely disappeared after long periods of slow decline. And that was the way extinction was understood for a long time. While scientists would hypothesize that global catastrophes might have been the culprit in mass extinctions, there was no evidence found until the 1980s. Because in the 1970s, geologist Walter Alvarez noticed that the only indication of the dinosaurs' extinction was a thin layer of clay, beyond which no dinosaur fossils could be found. And this layer could be found all over the world. Walter could not for the life of him understand how this thin layer of rock could contain the ingredients for the dinosaur's extinction. So he told his father about it. Luis Alvarez, Walter's father, was a Nobel Prize-winning physicist who not only discovered entire families of new particles, he worked on the development of the nuclear bomb and observed the bombing of Hiroshima and Nagasaki firsthand. With his father's expertise, Walter discovered that this thin layer of sediment that marked the dinosaur's extinction contained an unusual amount of iridium, an element rare on Earth, but common in asteroids. They also found evidence of soot, shocked quartz crystals, and microscopic diamonds, all indicative of a massive asteroid impact. The extinction of the dinosaurs was a catastrophe of such destructive power, it made the Hiroshima and Nagasaki bombs that Walter's father designed look insignificant. Despite all the evidence, the Alvarez hypothesis remained controversial. It wasn't until after Walter's father's death that an impact crater of the right size and age was discovered. Since then, the Alvarez hypothesis has become accepted in the scientific community as the most plausible cause of the dinosaurs' mysterious disappearance. And since then, many more periods of mass extinctions have been recognized in Earth's history. As many as 20 have been identified, but they are often grouped into 5 main extinction events, excluding the mass extinction event that is happening right now before our eyes and at our behest. Every day, dozens of species are estimated to be lost forever. As many as 140,000 species may be lost every year, and this loss is happening at 1,000 times the natural rate. Amphibians, birds, plants, fish, and invertebrates all have significant portions of their population at risk of disappearing from the planet. In the coming decades, we could expect to lose up to a fifth of all mammal species. The African elephant could soon vanish from the wild, just as their ancient cousins, the mammoth and the mastodon, did thousands of years ago. Habitat loss, environmental destruction, climate change, and rampant poaching have contributed to the greatest loss of biodiversity this planet has seen since the extinction of the dinosaurs. And in millions of years, if there's anyone around to look at the thin strip of sediment that represents our time on the planet, they'll be just as perplexed by the sudden disappearance of so many life forms as Walter Alvarez. Except there will be no impact crater to validate his finds, only us. Cuvier would have described the sixth mass extinction as a revolution. But unlike the French Revolution of his time, it's not being instigated in the name of liberty, fraternity, and justice. Instead, today's revolution is being fought in the name of short-sightedness, greed, and wastefulness. But most of all, this extinction has been made possible by the insistent refusal to accept what Cuvier undeniably proved. Life on Earth is not limitless. In fact, it's exceedingly fleeting. And the world we live in cannot be taken for granted. For eons, since the beginning of the solar system itself, a chunk of stone the size of Mount Everest spiraled around the sun. Tiny perturbations in its orbit and minor collisions with other planetary bodies sent it closer and closer to its inevitable fate. While the trajectory of that asteroid had been set since its creation, the mass extinction happening now is not preordained. It's not inevitable. It can be easy to despair in the face of problems this large, to see them as beyond our control, or too impossibly entrenched to change. But it all begins with a revolution in ourselves. Because what Cuvier proved was that the world could change, and that change could come about suddenly and powerfully. While what we do on an individual scale might seem inconsequential, so can each perturbation in the orbit of an approaching asteroid. Every little wobble counts, and eventually it can be enough to make an impact.
So, as you heard in the movie, but it's important, so I'm going to say more of it. He established the idea of catastrophism. He explained extinction by periodic revolutions or catastrophes had befallen on Earth. Each one wiped out a number of species, like the guy said, 5 big one, and we are probably in the 6th one, and hopefully we can change, then it will not happen. So Cuvier regarded these revolutions as events with natural causes and considered their causes and natures to be important geological problem. And he didn't think that we humans can learn about it more. It's absolutely independent from us, and we cannot stop it or we cannot start it. We cannot do anything, and we cannot really learn about that. That's why Cuvier tried to stop thinking about what causes it and how did it happen, which I think the curious mind has to go on. We need to want to know what happened when. So you shouldn't just shut your mind off. You have to start thinking critically and always ask why and what happened, because that way you will be able to solve problems, and it's really, really important that we do that. The next scientist you will have to know is John Jolly. He was living between 1857 and 1933. Madame Curie have discovered uranium and the radioactivity in about 1900. Jolly was still alive when they discovered radioactivity. However, they haven't started to use it yet for calculating absolute ages for rocks. He tried to calculate the age of the Earth using the salt content in the ocean. It was a pretty good idea. He assumed that originally the ocean was freshwater and became salty by the erosion of the different rocks around the ocean. You just need rocks which have sodium and chlorine, and when they erode into the water, they will become salt. So he calculated using an erosion rate he might have observed, calculated that the Earth has to be at least 90 million years old. As you know, if we compare that to the 4.6 billion, it's a very, very young age. The problem he had is that he didn't realize that a lot of the times the salt actually precipitates out of the ocean, and then the erosion has to happen over and over and over again to keep the same salt content in the ocean. So that's where he went off with the calculation. And we just finished the scientist I want you kind of to know, and now we have to start talking about the geologic time itself. You probably would think of time as minutes, seconds, months, years, probably even thousands of years. Not indefinitely, not in millions or billions of years like we have to. So we geologists have another measure of time. We have to think in millions and billions of years. When I was in high school, I went to a special geology high school. The first day of classes, my physical geology professor have told us that we have to think about geologic time compared to our lifetime. 1 million years in geology is equal with one blink of our eye in our lifetime. So now, if you think about the blink of your eye and how many times do you blink in your lifetime, even if you just sleep for 60 years, that would be 1 million years. So you can feel the waste of the deep geologic time. Another really good close proximity to the geologic time is if we compare it with a calendar year. Let's say New Year's Day is about 5 billion years ago. We would figure that January through October, which is more than three-fourths of the Earth history, is exceedingly obscure. Now, why is it? Because those rocks are so old that they have gone through like periods of metamorphism. Remember, metamorphism is the high pressure, high temperature changes in the original rocks. And if it happens more than one time, couple of times throughout the history, you cannot really recognize any original sedimentary or igneous rock texture or anything. So we can say that three-fourths of the Earth history is exceedingly obscure. The first recognizable fossil animals came about in mid-November. The extinction of dinosaurs occurred on Christmas Day. Can you imagine Christmas Day? And the Homo sapiens appeared, which is us, appeared at 11 p.m. on December 31st. So that's the very last day. And all the human history occurred in the last few seconds of New Year's Eve. So you see, this is like a really, you can touch almost deep geologic time by thinking about it like this. A bunch of you have already picked up some rocks, especially when you were little kids, and wondered about their age. Even it is possible, because I always tell my students the age of certain rocks, even possible that someone already answered to your question talking about hundreds of million years. Like, remember in the lab, if you were in my person to person class, I picked up a rock and I said, I told you that it was 400 million years old. And you just looked at me with big eyes and you didn't understand. How would I know? This is the cool thing that we're going to learn about it now, because the science which permits us geologists to describe the age of different rocks is called geochronology. And that's what we're going to talk about from now on. Geochronology as a science started about 400 years ago when Nicola Steno described how the position of strata in superpositional sequences could be used to show the relative age of the layers. Which one is older? Always the oldest should be on the bottom. If we look at this right here, see, the one which is on the bottom has to be the oldest, and these layers are younger because these guys were already here when they settled down. So we use two different time scale. One is this we were just talking about, the relative ages, and the other one is the absolute age, which we couldn't start using before the radioactivity came in, and then geologists realized that some isotope, radioactive isotope, can be used to define absolute age for different rocks. So we still use both of them because absolute ages are only really reliable for igneous rocks. So if we have any sedimentary rocks in the sequence, their ages we just know by the proximity of the igneous rocks. Of course, the early geologists must have used only relative ages because we didn't have the radioactivity, so they couldn't use absolute age data. They didn't exact way of knowing how many time units would be represented in the whole geologic timescale, nor could they know what fossils could be used to correlate from one location to the next location. Even the relative timescale grew as a puzzle in a very unsystematic manner. The geologic units were named after local geography. People didn't know where to put what. Today, they have a group of scientists who are controlling the geologic timescale. There are no changes unless the group goes through and they make a decision that it should be changed. So here we have the geologic timescale, which is the most accepted one. I want you to memorize this timescale because that way you will know what we're talking about. Because the second part of this historical geology class, we're going to talk about the actual times and we will say what happened when. So if you don't know it, it will be really hard for you to perform well on the test. So I'm going to show you here. This is interesting. So the 4.6 billion, 4.5 4 billion starts here at the Hadean, and these three brown time units are the Precambrian. Now it's really interesting to see because here they made a close up of the Precambrian. You can see that Hadean, Archean, and Proterozoic, and then the Phanerozoic, which is the whole geologic timescale as we know it today. That's much less than all the other three. There is a circle here showing that all this is Precambrian. Only the last 12%, the whole geologic time is what we really kind of know about. Okay, so this is very interesting. I need you to know it. And the reason that it's so low in terms of the geologic timescale is because we don't know anything about it. The more detailed area is where we know a whole lot, and that's the last 66 million years. You can see this last 66 million year takes a bigger room than the 490 million